In the last class, I defined this notion of packed learnability. Right? We saw that in general, the excess risk can be decomposed. The excess risk is basically the output or the risk achieved by a given learning algorithm minus the optimal risk, the base optimal risk. Right? The base optimal risk is the least amount of risk that you can possibly achieve even if you knew the joint distribution Pxy. So this excess risk can be decomposed as a sum of an estimation error, which is how far your algorithm does compared to the best predictor in the class, plus an approximation error, which is how far away is the optimal predictor within the class compared to the base optimal. Right? So this approximation error is purely a characteristic of the hypothesis class that you chose. And given the hypothesis class, the estimation error is purely a function of how good your learning algorithm is. So we'll focus on the first term, that is, we want to ensure that for a given hypothesis class, the estimation error is as small as possible. Because in general, you really don't have any way of finding out what this approximation error is beforehand. Because after all, you don't know what is the joint distribution Pxy. So your hope is to just choose a hypothesis class that is kind of rich enough, whatever that means. And then once you chose a good enough hypothesis class, you try to design an algorithm for which the estimation error is as small as possible. Right? And to make this more formal, I define this notion of packed learnability or agnostic packed learnability. So given the learning problem, which is defined by x, y, the domain set, the label set, and the loss function, we say that a given hypothesis class is packed learnable if for every epsilon and delta greater than 0, using a finite number of samples, that is, there is some nh finite which depends on epsilon and delta, such that given at least nh training samples, you can ensure that with high probability, with at least 1 minus delta probability, the risk or the estimation error is at most epsilon. Right? So another way of saying this particular statement is that the probability that R of Hs is less than or equal to R of H star plus epsilon is at least 1 minus delta. Right? So this is what we want to target. So for every epsilon and delta greater than 0, there should be some nh of epsilon comma delta, which is finite, and such that given these many samples, you can achieve epsilon delta error. All right. So if there is no such for a given small enough epsilon and delta, if a finite number of samples is insufficient to give you epsilon delta error, then it means that this hypothesis class is not packed learnable. All right. Similarly, we can specialize this to packed learning of a concept class, and particularly in the context of classification, we will demand that the probability that Hs of x is not equal to the ground truth f of x should be at most delta. All right. So now, given we also saw that the no free lunch theorem says that not every learning algorithm can be solved absolutely. It's not possible to get to do the absolute best all the time. So given any learning algorithm, if the number of samples is not enough, if it's less than the size of the domain set divided by 2, then there is some learning problem. By that I mean there is some joint distribution Pxy such that there is actually a predictor drawn from the space of all possible functions from x to 0, 1, such that this predictor achieves 0 risk, but no learning algorithm will be able to learn a predictor that does even close to this. All right. So no matter which learning algorithm you take, with high probability, that is with probability bounded away from 0, the risk is going to be at least some positive constant. All right, so there is no hope of achieving an arbitrarily small epsilon delta error. So as a corollary, we saw that if you have an infinite domain set, then and you take the hypothesis class to be the set of all possible functions from x to 0, 1, then it is impossible to achieve an estimation error that goes down to 0 even as you increase the number of samples. All right. So then if that's a negative result, then what can we actually show? That is, when is it actually possible to achieve pack learnability? And one sufficient condition for pack learnability is this notion called uniform convergence. So loosely speaking, uniform convergence says that given a finite number of samples, that is, a finite number of samples is enough to ensure that all of the empirical risks are arbitrarily close to their actual risk, the generalization errors. All right. And formally, we say that a given sample set of size n is epsilon by 2 representative if for every hypothesis within your class, every predictor within your hypothesis class, the empirical risk is epsilon by 2 close to the average risk. Okay. So it means that this particular sample set, this particular data set ensures that the empirical risk is a good representative of the true generalization error. And that's a good feature to have, because ultimately if you want to achieve a small generalization error, then all you have to do is choose a predictor which achieves a small empirical risk, because the empirical risk is a good representative of the generalization error. Right? And this also means that if you're ensured that the data set is epsilon by 2 representative with high probability, then the empirical risk minimizer is really one of the best algorithms that you can hope for. Right? Because what does empirical risk minimizer do? The empirical risk minimizer chooses that predictor from your hypothesis class which achieves the minimum empirical risk. All right. So if HS is the empirical risk minimizer, then just by the triangle inequality, you can see that the empirical risk minimizer achieves a generalization error, or in other words, estimation error, which is at most epsilon, provided that the sample is actually epsilon by 2 representative. Right? So the takeaway message is that if we are guaranteed some S that is epsilon by 2 representative, then empirical risk minimization is a good learning algorithm. Right? Question? Which one? Correct. Correct. Well, this is a consequence. Remember that S is epsilon by 2 representative, which means that R of Hs or R of Hs is epsilon by 2 away from Rs of Hs. Right? Remember that R of Hs is the average risk, Rs of Hs is the empirical risk. Right? You know that R of Hs, if S is epsilon by 2 representative, then R of Hs is at most Rs of Hs plus epsilon by 2. Correct? Great. Which now Rs of Hs is what? It is the empirical risk corresponding to the empirical risk minimizer. Right? So Rs of Hs is less than or equal to Rs of H star. Right? Remember that H star is the one that achieves minimum R. Correct? Rs could be a little bit different from R, because Rs is after all a random quantity. R is a deterministic quantity that depends on the distribution. So this quantity is R of Hs is at most Rs of H star plus epsilon by 2. It can't be any more. But the sample is epsilon by 2 representative, which means that R of H star is within an epsilon by 2 of Rs of H star. Alright, so this is less than or equal to R of H star plus epsilon by 2 plus epsilon by 2, as S is epsilon by 2 representative, which is exactly what I had in the previous slide. That is, R of Hs minus R of H star is at most epsilon. Is that clear?
H star is a better function.
H star is a better function. Correct.
Then we should have in second step should be less than or equal to H.
Which one? So again, remember that H star achieves minimum value of R, the average risk. But Rs is the empirical risk.
Okay, H star is better than Hs.
H star is better than Hs in terms of the average risk. Alright, so always R of H star is going to be less than or equal to R of Hs. Right? This is always guaranteed by definition of H star. But then if the sample is epsilon by 2 representative, then Hs is not too far away from H star. That's what this is saying. Alright. Okay, but remember, all of this is for a given sample. So this is what is a good data set. All right. If it's a good representative of the actual distribution. Now, in general, the data set is obviously a random quantity. So now we need to make a probabilistic requirement on the data set. So we say that a given hypothesis class satisfies the uniform convergence property or equivalently it is a Glivenko-Cantelli class if, again, basically all of the empirical risks converge uniformly to the average risks. So if for every epsilon and delta greater than 0, there is some positive quantity, some finite but positive quantity, and we'll call this NUC of epsilon comma delta. Let me call this, we use subscript h superscript UC, just to denote that it depends on the class H, and UC denotes uniform convergence. Such that the probability that S is epsilon by 2 representative is at least 1 minus delta for all n greater than or equal to this NH UC of epsilon delta. So it basically says that if, let's sort of write this down explicitly. This is the probability that Rs of H minus R of H is less than or equal to epsilon by 2 for all H within the hypothesis class. So this ensures that with probability at least 1 minus delta, all of the empirical risks for all of the functions within your hypothesis class are epsilon by 2 close to their corresponding average risks. Right. So basically this says well, we know that if the sample is epsilon by 2 representative, then ERM is going to find something that is epsilon good, right? So what this says is that if the hypothesis class is a Glivenko-Cantelli class, or it satisfies the uniform convergence property, then ERM is going to find the right solution with probability at least 1 minus delta. Right? So if H is a Glivenko-Cantelli class, or satisfies the uniform convergence property, then ERM is a pack learner. So essentially, if you are in a scenario where uniform convergence property holds, if you ever have a problem where the uniform convergence property holds, then the best thing you can do is just do ERM. That's good enough. This does not mean that the empirical risk minimization is the best learner for all problems. In general, if you have a classification problem where the number of classes is finite, then ERM is indeed optimal. But then if the number of classes is infinite, then ERM need not be optimal. There are multi-class classification problems where the number of classes can be infinite, where ERM is not optimal and you have to do something else. All right. But for many problems of interest, many supervised problems of supervised learning problems of interest, ERM is in fact pretty good, and that's why it's so widespread. So here is okay. So this ensures that if you have uniform convergence, then you have a packed learner. But then what can we say something more about the minimum number of samples required to guarantee an epsilon delta error, right? So we're not just interested in determining whether a given class is packed learnable or not. For a given class, we also want to characterize what is the minimum number of samples that you require, minimum size of the data set that you require in order to get at least a certain level of performance. I'm sorry? We'll see that. For what problems is VC optimal? And in fact, yeah, let's just wait a bit. All right. So here is, so before we look at it in a completely general framework, let's take a special case, more of an application of what we've seen previously. So if L is bounded, so when I say L is bounded, this could be an arbitrary supervised learning problem. It could be classification, it could be regression, but the loss function is bounded. All right. That is, there exists some M which is positive but less than infinity, such that L of h of x comma y is less than or equal to M with probability 1. Okay, so if the loss function is kind of bounded, then, and the hypothesis class is finite, or let me, so if L is bounded, then any finite hypothesis class is a Glivenko-Cantelli class. So this satisfies the uniform convergence property. How do you prove this? Correct. Yes. The empirical risk, well, need not be, right? The empirical risk could, the empirical risk is a random quantity, right? It could potentially be less than the average risk for some sample. Right? I'm sorry, which part? In the definition of pack learnability, there was no empirical risk appearing anywhere, right? So let's go back to the definition of pack learning. Yeah. The definition of pack learnability says that there exists some learning algorithm. It need not be ERM. In general, it need not be, ERM is not may not be the optimal algorithm, but all it says is that there is some algorithm which outputs HS. It takes, so the what is a learning algorithm? A learning algorithm is you can think of it as a black box that takes as input a data set and outputs a predictor. So the claim is that the hypothesis class is pack learnable, or the definition of pack learnability is that so H is pack learnable if there is some algorithm which takes S as input and outputs a predictor HS whose average risk is guaranteed to be within epsilon of the best possible average risk within this class with probability at least 1 minus delta. Alright. Now if the hypothesis class is a Glivenko-Cantelli class, or if it satisfies uniform convergence, then the empirical risk minimizer is guaranteed to achieve this. You can choose HS to be the empirical risk minimizer corresponding to the hypothesis class H. Does that make sense? Any other questions? Okay, so how would we go about proving such a statement? That if L is bounded, then any finite hypothesis class is a Glivenko-Cantelli class. In addition, we also want to characterize, in fact, and n the minimum number of samples to achieve epsilon delta error is at most some constant, some universal constant times 1 over epsilon square log the size of the hypothesis class divided by delta. Okay, how do we use Hoeffding's inequality? Okay, great. So first, we know that L is bounded, and the random variable that we are interested in bounding is basically the empirical risk, which is nothing but 1 over n times summation I equal to 1 to n L of H of xi comma yi. So this is nothing but a sum of IID random variables. So xi, yi's are all IID. We assume that the data set is an IID data set. We don't know what is the true distribution, but we certainly know that this is an IID data set. And we know that each of these L, xi, yi's, these are bounded random variables. Right? And we've seen that every bounded random variable is sub-Gaussian. Right? So then that's great, because I can use Hoeffding's inequality to say that for any fixed predictor, the probability that Rs of H deviates from R of H by an amount, let's say epsilon by 2, is upper bounded by 2 times universal const e to the power of minus some constant, which could depend on the bound m, but we won't really worry about that because the parameters that we are interested in are just epsilon, delta, and the size of the hypothesis class. Some constant times n epsilon square. All right, but this is for a fixed h. All right, what do we want to show? We want to show that for every h within the hypothesis class, r of h minus rs of h is less than or equal to epsilon by 2. Yep, so we can just use a union bound. So the probability that rs of h deviates from r of h by an amount epsilon by 2 for even one predictor in your hypothesis class. So this is the bad event, right? If you want uniform convergence to hold, or if you want the sample to be epsilon by 2 representative, then rs of h must be epsilon by 2 close to r of h for every h. And the bad event is that rs of h is at least epsilon by 2 far away from r of h for at least one predictor in the hypothesis class. All right, and what is the probability of this bad event happening? This can just be upper bounded by the union bound. And this is less than or equal to the size of the hypothesis class. So for every h in the hypothesis class, I have this holding true. So if I want to be a little more careful, then this is less than or equal to the sum over all predictors probability that rs of h deviates from r of h by an amount at least epsilon by 2. And we know that this is upper bounded by 2 times e raised to some constant times n epsilon square. So this is just the size of h to e to the power minus some constant times n epsilon square, where this constant could potentially will of course depend on the bounds on the loss function. We assume that the loss function is bounded, but we assume that the bound is something small. Let's say if we take binary classification with the 0-1 loss, the bound it's always bounded between 0 and 1, so I could just take that bound to be equal to 1. Now I want this quantity to be at most delta, right, to guarantee uniform convergence. So if I want this to be less than or equal to delta, then I want e to the power c n epsilon square to be at least 2 times the size of h divided by delta. So n is at least whatever, some universal or some constant times c epsilon square log 2 times the size of h divided by delta. Right, so as long as the number of samples is at least this quantity, with probability at least 1 minus delta, the sample is going to be epsilon by 2 representative. So this means that any finite hypothesis class is actually a Glivenko-Cantelli class, or it satisfies the uniform convergence property, and we have a reasonably good bound on the minimum number of samples required to guarantee an epsilon by 2 representative data set. All right. So this means that already we can say something about the learning algorithm. So if you have a finite hypothesis class, take any learning problem, not necessarily binary classification, could be, let's say, regression with some bounded loss function, or it could be classification with, let's say, the 0-1 loss or any loss function that is bounded. In all of these cases, you now know that if you have at least these many samples, then ERM is going to achieve epsilon delta error. All right. In all of these situations, you can achieve epsilon delta error. Now, is this really the minimum number of samples required to achieve 0 epsilon delta error? That's something we don't know yet. Potentially, there could be a better learner than ERM, and even ERM potentially could do better using the fewer number of samples. We don't know that yet. So really the question is there some measure of complexity of this hypothesis class that captures the minimum number of samples required in order to achieve a certain epsilon delta error? And this particular statement was only for a finite hypothesis class. So if your hypothesis class is infinite, then what do we do? Does it mean that you can't achieve uniform convergence, or it is not packed learnable? Or is there some other measure? Right? Okay. So now our goal is to find out what is it about a particular hypothesis class that characterizes packed learnability. Is there some feature about the hypothesis class that ensures that this is packed learnable or not? Certainly, if the hypothesis class is finite, then we know that it is packed learnable, as long as the loss function is bounded. And you can slightly relax the conditions on boundedness as well, as long as you have something like sub-Gaussian or sub-exponential loss function, you can still guarantee packed learnability. So finite hypothesis classes are fine. But most hypothesis classes that we are typically interested in are all infinite, right? Because you have some real parameter that you want to tune. As long as you have one real valued parameter, obviously the hypothesis class becomes infinite. Right? So is there some other characterization of packed learnability? So one sort of quick guess that you may try to make is that if the number of free parameters is finite, then it is packed learnable. Right? That's maybe a natural guess to make. That turns out to be not true. Even for the case of binary classification, you can come up with hypothesis classes with just one free parameter. In fact, we'll see that in just a little bit. There are hypothesis classes with just one free parameter, but this is not packed learnable. But you can also have hypothesis classes with many free parameters, but that is packed learnable. All right. So what property is there? Some structural characteristic of the hypothesis class that determines whether H is packed learnable or not. Yeah. Free parameter is, well, you have, let's think of the hypothesis class. So what is a hypothesis class? It's just a class of functions, right? Now, you need some way of defining this class of functions, correct? So one way of defining the class of functions is through certain parameters. You vary those parameters and you get all possible functions in the class. For example, if you take the set of all functions of the form h of x is equal to, let's say, indicator A transpose x greater than or equal to b. All right, this is the class of all linear classifiers. All right. Now here the free parameters are the vector A and the real value b. Now if A is, let's say, d-dimensional, then you have a total of d plus 1 parameters. All right. Similarly, if you take the function, let's say h of x is equal to indicator sine alpha x greater than or equal to 0. All right. This is also another hypothesis class. There's one free parameter over here. Alpha is, of course, I need to mention. So this is A in R to the D and B in R. In this case, I am taking alpha belongs to, I can just take R greater than or equal to 0. Let's say R greater than 0. This is another hypothesis class. In the first case, I have d plus 1 free parameters. That's what I say. That's what I mean when I say free parameters. And in the second case, there is only one free parameter. Only alpha, right? It turns out that the first example is pack learnable. The second example is not pack learnable. Even though the second example has just one free parameter and it looks like a simple class of functions. All right. It's just one additional non-linearity. So I have alpha x in the first example as well, but in the second it's just sine of alpha x, and this small modification turns out to completely change the learnability property of the hypothesis class. All right. So then what is it that characterizes pack learnability? It turns out that this is not a completely well understood problem, although a lot of developments have happened in very recent years. For binary classification, it's a very well understood problem. So for binary classification, it turns out that there's a parameter of the hypothesis class, or it's a combinatorial parameter of the hypothesis class called the VC dimension that determines whether a hypothesis class is pack learnable or not. So this is the Vapnik-Chervonenkis dimension, or the VC dimension. It turns out that for binary classification problems, the hypothesis class is pack learnable if and only if the VC dimension is finite. So if you have a hypothesis class with any number of parameters, or it could be an infinite hypothesis class, but as long as the VC dimension is finite, it is pack learnable. And you can also get an upper bound on the sample complexity, or the minimum number of samples required to achieve an epsilon delta error in terms of the VC dimension. And likewise, if the VC dimension is infinite, then this is not pack learnable. So it's a necessary and sufficient condition for pack learnability for binary classification problems. Now, for multi-class, it turns out that things are a little more complex. For a long time, people believed this another combinatorial parameter called the Natarajan dimension.
Sir, when we said this class is finite,
Yeah.
do you mean that number of parameters of it are finite?
No, the number of functions in the class is finite. So in the examples that I've given over here, both of them have a finite number of parameters, but the hypothesis class itself is infinite. Because there are infinitely many distinct functions in this class.
When we said the first one is backloadable and second one is not backloadable.
So I was only referring to these two examples over here. Both are infinite hypothesis classes, right? This one is an infinite hypothesis class. The second one is also an infinite hypothesis class. Both of them have a finite number of parameters, finite number of free parameters. But this is an infinite hypothesis class that is backlearnable. The second one is an infinite hypothesis class that is not backlearnable.
So this made you conclude that finiteness of a hypothesis class does not guarantee backlearnability.
No.
It's something else.
Finiteness of a hypothesis class guarantees backlearnability. Finite number of free parameters does not guarantee backlearnability. Because the parameter could range over infinitely many values, right?
Each
In-
value maybe represent each
Correct.
value
Each parameter could be a real value, right?
it belongs to R, so it gives an infinite class.
It gives an infinite class.
Okay, so then you said it instead of saying that finite parameters does not guarantee backlearnability, you
Correct.
said finite VC dimension or binary classification
Guarantees backlearnability, yes. And infinite VC dimension implies that the class is not backlearnable. So the class is backlearnable if and only if the VC dimension is finite
for binary classification.
for binary classification.
Sir, where does this notion of loss function, like, is it like we feed in the system that this is the loss function we are taking?
Yeah, we determine. When we specify the problem, we say that when we define the learning problem, there are three things that we have to specify. One is what is the domain, what is the label set, and the third is what is the loss function. How are you going to determine whether something is good or not? Because you need a measure of performance, right? And that's determined by the loss function. You have to specify what that is.
So is there any case we can bound the values taken by three parameters such that we can get a finite hypothesis class?
Again, it depends. So even this, see, the problem with the notion of free parameters is that you can always change the way you have the number of parameters and so on by reparameterization in principle, right? You could always do that. These are simple cases where it's easy to see things, but in general, when you have more complicated functions, the exact number of free parameters, you could reparameterize things in a different way to have a different number of free parameters.
Yes, we are just transform.
We can always transform the same function class from one to the other, right? So really, the number of free parameters is not a good measure to determine whether something is backlearnable or not.
Sir, and also did we from the previous understanding of uniform learning property included if H is finite and
Correct.
if loss function is bounded,
Correct.
then H is agnostic backlearnable.
Correct.
But I have a question: if loss function is not bounded,
Uh-huh.
can you give an example?
So as long as the loss function, let's say, decays very fast. So ultimately, what did we need in order to prove this uniform convergence property? To prove the uniform convergence property, we needed some kind of a tail bound. Right? As long as we have any such tail bound, we are good. In fact, I don't even need an exponential tail bound to prove backlearnability.
This is sub-Gaussian.
This is a sub-Gaussian tail bound. But in principle, as long as this, even if the variance of this is finite, right, that's enough, because I could potentially just use Chebyshev's inequality. and then use a union bound. The bound that I get is very loose, but it still guarantees pack learnability.
What should I say? Like loss functions will satisfy which property such that.
As I said, as long as this variance, the variance of this particular random variable is finite, that's good enough.
How do we say mathematically?
So, I mean, what is the quantity of interest, right? This is the loss. This is the loss function. This is a random variable of interest. If this loss function has finite variance, then it is pack learnable. Again, it's a sufficient condition. It's not necessary.
Yeah, it's sufficient.
It is sufficient. That's a more general sufficient condition than the loss function being bounded. But if you have something more complicated, then it's maybe going to be difficult to characterize the sample complexity.
And why do we say Glivenko-Cantelli class property as uniform convergence property? What is happening here? What is uniform convergence here?
So uniform convergence means that the empirical risk is converging to the average risk uniformly. When I say uniformly, it means that for all the functions in your class, the rate of convergence of the empirical risk to the average risk is the same. So remember, what we have here is, let's take a look at this quantity, right? This says that for any fixed h, right, for a fixed h, the Rs of h converges to R of h at an exponential rate. Right? When I say rate, it's as a function of the number of samples. All right. Now, in general, we didn't worry too much about this constant c, but potentially this rate of convergence could depend on h. All right. Now, what we want is that this convergence happens for every h at the same rate. Because here what we had to resort to was a union bound. If we could somehow guarantee that this convergence happens for all functions at the same time, then we are done. That's exactly what it means to have uniform convergence.
And then we are saying uniform convergence guarantees pack.
That's why uniform convergence guarantees pack
It won't
learnability.
hold for infinite. Okay, it might not.
It may hold, it may or may not hold for an infinite class. Because for a finite hypothesis class, I could just use the union bound. That's good enough. For an infinite class, I can't use the union bound because I have to take union over infinitely many terms. Right?
Sir,
Yeah.
like let's suppose we take the loss function as the absolute difference.
Okay.
So does it mean that for like as in we feed the inputs, like for every corresponding xi we get a yi, so will the hypothesis function adjust itself accordingly to minimize it? Or is it like we are doing it for all the hypothesis functions and then taking the minimum?
Let me maybe try to understand your question first. So you're saying that your loss function L of y hat is
Yes, sir.
absolute difference between y and y hat. Okay, and what is y? So what is the label set?
But, like it may be a binary classification problem. Like,
Okay, then loss function is bounded, right? Is that what you wanted?
like is it possible that we have a loss function which is bounded, but like the difference between h of xi and yi,
Correct.
it becomes unbounded, but then also it remains pattern.
Yeah. So as I said, this boundedness was a sufficient condition. All right. As we just discussed, we don't even need boundedness. We could potentially, as long as the variance of L of even this is sufficient. The variance of L of h of x, comma y, if this is less than infinity, then this is pack learnable. because instead of using Hoeffding's inequality, I just use Chebyshev's inequality. That's good enough. Right? Or some as long as I'm able to use a tail bound, I'm fine. But again, all of these are sufficient conditions. Just because I'm not able to prove it using a tail bound doesn't mean that it is not pack learnable. It's easier to prove that this is pack learnable rather than say that it is not pack learnable. All right. So
Whenever you in this class you say pattern, but you
Correct.
implies agnostic pattern.
I generally say I mean agnostic pack learnable. That's right. I'm using those two terms sort of interchangeably for now, but because just hold on to that thought for a little bit. We'll see why
Agnostic pattern is a generalized version of pattern.
agnostic pack learnability is a generalized version of pack learnability. Correct. No, so it's possible that a particular hypothesis class is pack learnable but not agnostic pack learnable. That is possible. But we'll see in the context of binary classification that that's not true. If it is pack learnable, it's also agnostic pack learnable. So the binary classification problem is kind of nice and special. Okay, so coming back to see what parameter of the hypothesis class or what characteristic of the hypothesis class characterizes pack learnability. For binary classification, it turns out to be this combinatorial quantity called the VC dimension. We'll explore what is the VC dimension, define it, and so on. But just for your information, for multi-class classification, the Natarajan dimension plays the role of the VC dimension for finite classes. As long as the number of classes, that is the label set, is finite.
So it means that like the multi-class classification can be considered as binary classification for separate labels.
Uh,
Where it's matching or it's not matching, right?
I didn't
So
maybe
for
understand.
binary classification, you usually between 0 and 1 you choose your output
Correct.
will be 1.
Correct.
So multi-classification across each output, let's say there are 4 outputs.
So there are two different. So multi-class classification is a bit of a loaded term. There are two different ways of approaching it. One is, let's say that the output is you have, let's say, 3 different outputs, each being a binary class. That's one way of formulating it. The other is the output itself is, let's say, a positive integer between 0 and 10. For example, if you're trying to classify handwritten digits, right, like the MNIST data set, for example, the number of classes is 0 up to 9, so there are 10 classes. Right? So the size of the label set is 10 in this case. And if we want to ensure that it always outputs, we're again considering the 0-1 loss, which means that we want y equal to y hat.
So what is the first one?
Which one? The first is, again, there are two different ways of looking at it. That, let's say, it outputs a vector.
Yes.
Okay, so and each element of the vector is +1 or -1. For example, let's say that I have an image. I want to say the following: does this image contain a cat or not? Does it contain a dog or not? Does it contain a car or not?
Okay.
That's one thing. All right. Again, all of these can be, in a sense, you could look at it in the same way, right? Because if it's a vector containing of dimension 3 and each entry can take +1, -1, then there are total 8 possible outputs. So you could just relabel it in a different way. All right. But I mean, there are reasons why people look at these things in using different approaches, but let's not worry about that. Effectively, for us, as long as this space, the label set is finite, then they're all the same. Because as long as this quantity called the Natarajan dimension is finite, it is pack learnable. If it is infinite, then it is not pack learnable. All right, but this does not hold for a very long time. It was believed that even if the class is infinite, then the Natarajan dimension classifies pack learnability. But it turns out that that's not the case. Very recently, people have proposed another notion, another combinatorial quantity called the DS dimension.
Sir, I have a question.
Yeah.
Because you're talking so much about pack variability, I have a question. If hypothesis is not pack variable,
Yep.
what are the bad consequences of it? It means I can't learn.
Yeah, you can never you can never achieve a small enough epsilon error, right?
Should I just ditch that class and just take some other?
Yeah, basically you should probably, if let's say you're doing binary classification, and it turns out that this class is not pack learnable, the hypothesis class is not pack learnable, then it means that you should probably change your hypothesis class. Right. Because it means that increasing the number of samples is not going to get you to the target. No matter how many more samples you take, you are never going to achieve a small enough error.
Okay, so it means that let's say if I'm going to algorithm using neural networks as my, let's say two layer neural networks as my hypothesis class.
Fine.
And theoretically I'm able to say that, okay, it is not pack learnable.
Yeah, let's say that you have some weird neural network class which has, let's say, infinite VC dimension.
Okay, yes. And it is not able to, so it's not pack learnable.
So it is not
Means
pack
that
learnable.
If I'm just not, if I just jump to practical, not theoretical,
Even then, so theory says that it is impossible to do so, which means that no matter what algorithm you take, you will never be able to guarantee a small enough error.
yes, but what will be the consequence in the practical? It means that will I get less, I will get lead to, it will lead to less generalization, or will it lead to less training errors, training accuracy?
You could potentially have a really small training error by just increasing the number of samples. That is always you can do, right? Because you can always have a small enough empirical risk. You keep increasing the number of samples, you could make the empirical risk sufficiently small. But your generalization, no matter what you do, how many more samples you take, the generalization error is never going to become arbitrarily small.
What this are
There you will hit a particular bound. Let's say you are never going to beat 70% accuracy, no matter how many more samples you take.
when this happens in my practical life, it means that
Yeah.
I have done something wrong. I should just model the problem using some different architecture.
Yeah, so basically you change the architecture.
So, practical life.
All right.
It's
Yeah. So again, all of these quantities, the VC dimension, the Natarajan dimension, DS dimension, all of these are combinatorial quantities which are in general not hard, not easy to compute. Right? They could be in like for nice simple functions, they're easy to compute. For hypothesis classes that are a bit complicated, let's say convolutional neural networks, they're not easy to compute. These are not easy quantities to compute. But for many functions, even that are, let's say, mildly complicated, you may be able to say that the VC dimension is finite or not. Which would mean that in many applications that's enough, because it means that you can solve the problem just by increasing the number of samples. Or if you are able to say that the VC dimension is infinite, then it means that there's no point in taking more number of samples if you want to achieve, let's say, 99% accuracy. You should just, it's better to just leave that and take a different hypothesis class. Right? So for multi-class classification, very recently people have proposed a different notion of dimension. This is by Danieli and Shalev Schwarz, one of the authors of one of the references that we're using. So they proposed this notion called the DS dimension, and very recently people have shown that for multi-class classification with infinite number of classes, the DS dimension characterizes pack learnability.
So just curious,
Yeah.
how recent it is?
So the DS dimension was proposed sometime about certainly after 2015. but that it characterizes multi-class classification came out in 2022 or so. So it's fairly recent. Right? The Natarajan dimension goes back to, let's say, 90s or so. The VC dimension goes back even further. All right, because for multi-class classification, finite VC dimension turns out to be insufficient. All right, and in all of these cases, so another result is that in these cases, where the VC dimension or the Natarajan dimension is finite, ERM turns out to be good enough. So ERM is a packed learner. But there are examples of multi-class classification where the DS dimension is finite, the Natarajan dimension is infinite, and or whatever, the DS dimension is finite, where the number of classes is infinite, where ERM is not the optimal learner. And the reason why ERM does not happen to be the optimal learner is that in these cases, the uniform convergence property holds. But there are situations where you have multi-class classification with infinite number of classes, where the uniform convergence property need not hold. So there are learners which are better than ERM for such problems. But in many problems of interest, the number of classes is usually finite. Let's say you're trying to find handwritten digit recognition or so on. The number of classes could be large, let's say 10 or 20 or 30 or 40, but still it's typically finite. And in most of these cases, the uniform convergence property holds, and therefore you might as well just use ERM. But as we'll see maybe later in the course, there are other ways to design a good learner. One is, of course, using ERM, but there are other approaches like boosting and so on, wherein you can take a bunch of weak learners, combine them to get a good learner. Okay, so this, the VC dimension, all of this, these combinatorial notions of dimension happen to characterize packed learnability, and they also characterize the sample complexity. That is, you can upper bound the sample complexity using some function of the VC dimension, the Natarajan dimension, and so on. All right, we'll soon see another measure of complexity. Which one? Okay, good point. So again, there's another notion of dimension called the fat shattering dimension in the context of regression. Again, these are all like combinatorial quantities which characterize learnability. Again, regression with under certain assumptions on what a loss function you use. So these are all whatever combinatorial quantities that determine whether something is packed learnable or not. Now, for all of these cases, it turns out that there's a more general measure of complexity, which is not combinatorial in nature, but which actually characterizes learnability. All right, something called the Rademacher complexity, and this Rademacher complexity is good enough. It's a good measure of, or it upper bounds the pack learnability or the sample complexity in all of these cases, the finite class classification case, the infinite class classification case, and so on. As long as you have uniform convergence, whether it's regression or classification, the Rademacher complexity is sort of a uniform, a universal quantity that gives you a bound on the minimum number of samples required to achieve an epsilon and delta error. Okay, but before we go over that, let me just define what this VCE dimension is, and we'll see a couple of examples.
Sir, I have this curiousness. When we say dimension,
Mhm.
are we referring to the bad hypothesis spaces over the S?
No. It's purely so the VC dimension. Let me just define this because that will make it more concrete. Right. So we're given a hypothesis class H, right? It is some collection of functions from x to y. Some collection of functions. It could be parameterized. It need not be parameterized. Okay. So let's suppose that I take now the domain set X. It could be finite. It could be infinite. Doesn't matter. So let's take some subset of the domain set such that which has exactly m elements. So for any subset of X with exactly m elements, we can consider the restriction of H to xm. All right. Of H to this particular subset. Let me call this H subscript xm. There are exactly m points, so this is, you can just represent it as a vector of length m, which is, what is the output of H of? So it's a collection of vectors. Let's suppose that xm is just x1, little x1 through little xm. So this is just a list of H of x1, H of x2 up to H of xm, where you vary H throughout your hypothesis class. Okay. Now again, maybe let me be a little more precise over here. When I say VC dimension, we're explicitly talking about the binary classification problem. All right. So I'm only looking at functions from x to 0, 1. Okay. Now the hypothesis class could be as large as you want. But suppose I pick m vectors. What is the size? What can be the size of H xm? Yeah, 2 power m, right? Because this is basically a collection of vectors, and each H of xi can take either 0 or 1, only 2 different values. So this is the largest size of H of xm is just 2 to the power m. There can't be any more distinct number of vectors in this class. Okay, so we'll say that the hypothesis class H shatters some subset xm if the restriction consists of all of these possible vectors. So the size of H of xm is exactly 2 to the power m. All right. So basically, if I take these m points, then as I vary h, I get all possible labelings of these points, of these m points. All right. So, for example, if let's say I take, I want to classify, say, 2 points in R2 using linear classifiers, right? I could achieve this by, right, if I take this particular classifier, then one side is labeled 0, the other side is labeled 1. If I take this particular classifier, then again, when I say, let's assume that in some sense the left side of the hyperplane, I'm using left quite loosely over here, is labeled 1 and the right side is labeled 0. All right. So in one particular orientation, right. So all of I can obtain all possible labelings by varying across the hyperplanes. Right. I can obtain 0, 0, 0, 1, 1, 0, and 1, 1. So if I take the space of all possible linear classifiers and I take any 2 points in R2, then H shatters this particular pair of points. Okay, is that okay? So this is what it means to shatter. Basically, it can produce all possible labelings, all combinations of labelings of this particular set.
Or equally, say that any binary classification, you can find the separate.
Not really. So we're trying to find out how rich the description is. Right? How many different possible labels can we generate for this set using the hypothesis class? Okay. So to give some intuition, let's say that I take 5 points and I am not able to produce all possible labelings. All right. Let's take 2 different hypothesis classes. Let's say for 5 points in one hypothesis class, I am not able to generate all possible labelings. In the other hypothesis class, I am able to generate all possible labelings. All right, for any collection of 5 points. Then intuitively, it would seem that the second class is a richer class or a more complicated class compared to the first one. All right, that's what intuition tells us. That's believable. Right? And that's exactly what is characterized by the VC dimension. Right? How rich the class is. So the VC dimension is the following. So the VC dimension is precisely the size of the largest subset xm subset of x. Let me just denote this x prime subset of x that is shattered by h.
What is the cardinality of x? It can be anything.
I'm sorry?
What is the cardinality of x?
So x could be infinite.
Yes.
I mean, that's when it is interesting.
Yes. When we take a subset which is a finite.
Correct. We are always taking finite subsets of this domain set. So in the previous example, right, in this linear classifier problem, the domain set is infinite because it is all of R2. Whereas I'm picking, let's say, 2, 3, or 5 points, which could be arbitrarily chosen. For every point, I can determine whether whether H shatters that set or not. Okay, fine. So the VC dimension is precisely the size of the largest subset that can be shattered by the hypothesis class H, which means that if the VC dimension of H is equal to D, then there should be at least one XD X1 through XD, which is a subset of X that is shattered by H. Basically, it is possible to generate all possible labelings of these D points using the functions in my hypothesis class. And secondly, no X D plus 1 can be shattered by H. So no matter how you choose the D plus 1 points, there are in general infinitely many ways of choosing these D plus 1 points. So no matter how you choose these D plus 1 points, it is not possible to generate all possible labelings using the class of functions that we have.
So when we say that the hypothesis class shatters set,
Correct.
then does it mean that every function of the hypothesis class does it, or is it like just at least one of them?
No, so you vary over all possible functions, right? You fix the set, you vary over all possible functions and see how many distinct labelings you can get, right? Let's see some concrete examples. We're almost out of time, but let's see just one example perhaps. So the first example is, let's say, the threshold functions, which is, let's say x is R, so it's the real line, and the hypothesis class is the set of all functions which can be written as indicator x greater than or equal to alpha, where this parameter alpha can be varied over all of R. Right? All right. So the function basically is just a step function, right? H of x is just a step function. It's equal to 0 for x less than alpha and equal to 1 for x greater than or equal to alpha. Right? So let's take one point. Is this one point going to be shattered by x, shattered by H? Let's take an x1. Take any point, doesn't matter. Is there a function H such that this point gets 0 and some other function H prime such that this gets 1? Yes, right? You just take alpha, let's take this to be x1. You take any alpha less than x1, you get the value 1. You take any alpha greater than x1, you get 0. Right? So take any single point, it is shattered by H. Correct? Let's take 2 points, x1 and x2. Can I generate the labeling 0, 0? Yeah, because I just take alpha to be greater than x2, I can generate 0, 0. Can I generate the labeling 1, 1? I can, because I just take any alpha which is less than x1. Both x1 and x2 are going to be labeled 1 and 1. Can I generate 0, 1? Yes, you take an alpha that is in between x1 and x2, you get 0, 1. But can I ever generate 1, 0? You can't, right? Because for x1 to be labeled 1, I should have an alpha that is strictly less than x1, which means that x2 is going to be labeled 1. All right. So, and this holds true irrespective of how I choose x1 and x2. As long as I choose two distinct x1 and x2, it's impossible to generate 1, 0. Yeah, it's impossible to generate 1, 0 using threshold functions. So x2, no x2 is shattered by h. So what can you say about the VC dimension? It's 1. So the VC dimension of these threshold functions is exactly equal to 1. So let's stop here, but one point that I would like to make is that for the VC dimension to be equal to D, it is enough to have one subset of size D that is shattered by H. It doesn't mean that every subset of size D or smaller than D has to be shattered by H. All right? Okay. So just to think along similar lines, here's another exercise. Just consider the set of all functions. Again, the same domain set, h of x. Suppose I have two thresholds. That is, it's equal to 1 if x is, let's say, greater than or equal to alpha but less than or equal to beta. What would the VC dimension be? Yeah? Yeah. So firstly, every single point, every singleton is shattered. You take any pair of points, this will also be shattered because we just have to resolve this particular case. So you take any function that looks like this is going to be shattered. Right? But you can't generate all possible points. In particular, if you take 1, 0, 1, if you take any 3 points, then you will never be able to generate 1, 0, 1. Because once h of x becomes 1, it becomes 1, it remains 1, and then once it becomes 0, it can't become 1 again. All right. You can, yeah? 0, 1, 0 you can generate. Right? You just choose alpha to be greater than x1 but less than x3. You'll get 0, 1, 0. So all of these h of x, they look like these pulses. All right? That's what you need to keep in mind. So try to generalize this to a case where you have, let's say, a union. So this is basically indicator over some interval. So h is set of all h of x, which is equal to 1 if x belongs to, let's say, alpha 1, beta 1, or alpha 2, beta 2, and so on, alpha k, beta k, and 0 otherwise. Try to think about what the VC dimension of this would be. Just take, let's say, k equal to 2. All right, two intervals, union of two intervals. So it basically consists of all functions that can be written as let's say 2 pulses. Okay.
So what is the intuitive meaning that H cannot shatter Xn? What is the intuitive application that H cannot shatter Xe?
Not sure what is the application of it.
What is the intuitive physical meaning? Our physical meaning, we understand. I'm not able to generate the labels, all the labels for the employees.
Correct.
But what is the application?
For a given set, it's not, I don't think of any intuition. But if it is not possible to generate all possible labelings, then one intuitive way of thinking about it is perhaps that there's less confusion as you get more number of points. Right? Because you can't see all possible labelings, some labelings can be eliminated. I'm sorry? It will be 2k minus 1. Okay, so let's stop here.